Okay, what we did last time is that we were looking at the idea of Nash equilibrium, and we identified games within which there were multiple Nash equilibria. And I introduced to you this idea about a focal point. So in these games of multiple Nash equilibria, remember, in a game that we've set up, we've already defined the Nash theorem. We said in every finite game, there must be at least one Nash equilibrium. But in some games that we saw, for example, when we saw Battle of the Sexes, we had a Nash equilibrium where they both went to the prize fight. We had a Nash equilibrium where they both went to the opera. So there are multiple Nash equilibria. Sometimes, though, there are certain things within the society within which we live, the psychology of players, institutional factors that lead us towards certain outcomes. And we went through a number of examples last time that we defined as focal points. Something within the nature of the game itself, something within the nature of society that leads us towards certain outcomes. And we went through a whole host of examples. And when I drew that back to Battle of the Sexes, I said, well, think about it. We had these two outcomes. One where they both went to the prize fight, and when they both went to the prize fight, the man achieved his most preferred outcome. But when they both went to the opera, that was our other Nash equilibrium, the woman achieved her most preferred outcome. And I asked you the question when we saw that game first of all, well, which one of these is more likely? And the simple answer is, neither of them was more likely. But then after we've been through this discussion of focal points, and then I threw in that bit of extra information, well, what would happen if the woman were the dominant personality in the relationship? Isn't it then much more likely that we'd observe the Nash equilibrium where they both went to her most preferred outcome, where they both went to the opera? So in that sense, opera would suggest itself as more likely, would suggest itself as a focal Nash equilibrium. And then when we extended that to the game that we saw of the stag hunt, again, there were two Nash equilibria. It was a game with multiple Nash equilibria. One, where both of the hunters pursued the stag. The other, where they both went off and chased rabbits. So again, there were two Nash equilibria. But in that game, I said one of these actually is more likely. And the one that was more likely was where both hunters pursued the stag, because both of them would be better off. So it obviously is a superior outcome. And in that sense, it would suggest itself as more likely, because unequivocally, both players are better off. And pretty much that's where we finished last week. But before this week, or before I start for this week on our next topic, which is going to be mixed strategies, I want to finish off this topic on Nash equilibria, and I want to just finish on this idea about focal points. Because what I've suggested to you so far is if we have a game where there are multiple Nash equilibria, and one of those Nash equilibria is better, where the players are better off, where it's superior, I've seemed to suggest for the moment that that Nash equilibrium will be more likely, as we've seen in that game of the stag hunt. However, what I want to do is give you an example this morning, another example that would suggest, again, in a game with our multiple Nash equilibria, that you shouldn't always think that the superior outcome will be the observed outcome. And the example I want to give you is something that's going to resonate with all of you, and that's the idea of how keyboards are set up. So, the way in which I want to frame this is just give you a little bit of history, first of all. So if we go back to the late 1800s, there was no standard way that the keys were arranged upon keyboards. Just no standard way at all. So you bought a typewriter, it would have an arrangement as dictated by that manufacturer. Then, in 1873, Christopher Scholes helped design a layout on keyboard, which you'll all be familiar with, which became known as QWERTY. Now the whole point about QWERTY is that it did something very special. It was designed for a very, very special purpose. And the reason it was called QWERTY is because of that first 6 characters along the top row. Now the question is, I want to ask you for the moment, and I'll quickly use, just so you can all get your phones out and see they've got QWERTY on them, I'm just going to ask you a very simple question of why you think QWERTY was invented. Well, the reason this was invented was actually not to minimise the distance, it was actually to maximise the distance between the most commonly used keys. Now the reason, obviously that isn't something that I'm going to ask you to reproduce in an exam, though that piece of useless information there, so don't worry about that. But the reason that this keyboard was designed, that arrangement with keys was designed, was to slow typists down. The problem at this time, we had manual typewriters, and typists were typing too quickly. And if they typed too quickly, the keys used to jam. And so, something was needed to slow typists down. And that QWERTY did that. It took the most commonly used keys, and it maximised the distance between them. So typists' fingers had to travel a longer distance. And that was designed to slow typists down. And in its day, this was an excellent solution. So much so that by 1904, the Remington Sewing Machine Company began the mass production of typewriters using this exact arrangement of keys. And so effective was this at slowing it down, and so widely used that this arrangement of keys on the keyboard became an industry standard with the mass production post-1904. Now, this in itself seems a little bit strange, but I've mentioned, okay, you've got Christopher Scholes, you've got the Remington Sewing Machine Company. These are things hundreds of years ago. And the reason it was invented was to slow typists down, to stop keyboards from jamming. And yet, with computer keyboards, with smartphones, do you need to slow yourself down? Is your keyboard going to jam because you type too quickly? Obvious answer is no. And yet we still use that exact arrangement of keys on a keyboard. This is in spite of the fact that alternative keyboard setups have been devised that aid typing, that allow typists to type more quickly. An example is what's known as DSK, Dvorak's Simplified Keyboard. This means that with this particular arrangement of keys, typists' fingers move up to or over 50% less distance. They can type more quickly. So exactly the same material can be typed between 5 and 10% more quickly. So in that sense, it's a more efficient industry standard. And yet, we don't use it. Now, the question is, why is that the case? Well, I've already introduced this idea. I've bandied that term about being an industry standard. Now, the important consideration of an industry standard, and it doesn't matter what it is that everybody, or virtually everybody, does the same thing. So, who drove their car in today? Who drove in? Yep, got the back. Okay, Scott, when you drove in, did you drive on the left side or the right side? Left, okay, that's a good answer. You drove on the left. Given that you were driving on the left, where was everyone else driving? On the left, okay. Not a difficult question so far. Did you have an incentive to drive on the right-hand side? No. If you did drive on the right-hand side, would you have had an incentive to switch back to the left? Yep, right answer again. So, what we've identified here is a Nash equilibrium. When Scott drove his car in today, he had an incentive to choose an optimal strategy, to drive on the left-hand side of the road. If he chose to drive on the right-hand side of the road, he would have had an incentive to deviate, because he would have been crashing into everybody else. So you can see, this is exactly the same as an industry standard, where everyone does the same thing. But in that sense, though, an industry standard is a Nash equilibrium. If you're not doing the same thing as everybody else, you have an incentive to deviate. If you're not doing the same thing as everyone else, that cannot be a Nash equilibrium outcome. Our definition of a Nash equilibrium was none of the players within the game have an incentive to deviate. You have an incentive to deviate, to do something else, that can't be a Nash equilibrium. So in this sense, everyone driving on the same side of the road is a Nash equilibrium. Well, that's exactly the same when we talk about keyboard technology. So in the parlance of what we've said here, we have two Nash equilibria. One where everyone uses QWERTY, but one where everyone uses DSK. The industry standards, and as long as we do the same thing, they are Nash equilibrium outcomes. But if you look at these two Nash equilibria that I've defined, one of them is obviously superior. The one where we all use DSK is superior to the one where we all use QWERTY. Yet before, when I talked about the stag hunt, we had two Nash equilibria. One where they both went chasing off rabbits, other where they both pursued the stag. And we said the superior outcome, where they pursued the stag, suggested itself as focal. That's the one that we would observe. And yet, the Nash equilibrium that we observe in terms of keyboard technology is obviously the inferior one, the one where we all use QWERTY. So, question is, why does that happen? Well, it all boils down to that historical precedent and the mass production in 1904 of typewriters using that QWERTY layout by the Remington Sewing Machine Company. Because of that historical precedent, that mass production, the typewriters that were produced, virtually all, had that QWERTY arrangement of keys. And then what did that mean for typists when people started learning to type, when they had these typewriters? Well, they then learnt to type using that QWERTY arrangement, and that's what they're used to. Hence, when these typists need to get typewriters, what do? They then buy them from manufacturers who produce that QWERTY layout. And hence, that's an incentive for manufacturers to produce QWERTY keyboards. And so that's what they did. And because manufacturers then produce these QWERTY keyboards, we then complete this virtuous circle here, where therefore almost all typewriters use QWERTY. And then we get locked in to this inferior technology. And this is known as the bandwagon effect, where everyone jumps on the bandwagon. Everyone follows exactly the same social norm. As an individual, we have no incentive to deviate, to do anything different. Collectively, as a society, it would benefit us all. We all got together and switched to this alternative superior technology. But it doesn't happen. Whilst it would benefit society, no individual has an incentive to incur the costs themselves. They just follow the social norm and do the same as everybody else. And hence, we get locked in to this inferior technology. And this phenomenon, the bandwagon effect, is an easy example of why certain Nash equilibria will be observed, will be focal, even though they are obviously inferior. The bandwagon effect. So, that concludes our discussion of focal points. The last thing I want to do to conclude our discussion of Nash equilibria and our first two topics in general is drawing out this distinction between what are known as strict and non-strict Nash equilibria. Now, I've not told you, but every single Nash equilibrium that I've given you up until this point has been a strict Nash equilibrium. If we go, or if you revisit all of the games, you will see these Nash equilibrium outcomes that we've identified. If a player deviated, that player would be worse off. And hence, would that player have an incentive to deviate? If you do something different, you're worse off. You have no incentive to deviate, which is fine. But you don't have to be worse off for it to be a Nash equilibrium. All that's required is players have no incentive to deviate. But does that mean you need to be worse off? It doesn't. We can also phrase it in terms of as long as a player is no better off. So if we've got a Nash equilibrium outcome, players have identified these optimal strategies. If a player can get a higher payoff by deviating, that's what they would do. Therefore, it can't be an optimal strategy. It couldn't be a Nash equilibrium. But if they had a lower payoff, is there incentive to deviate? No. If they have exactly the same payoff, if they're no better at deviating, again, is there incentive? Again, the answer is no. And it's that subtlety around that incentive to deviate that draws that distinction between a strict and a non-strict Nash equilibrium. And to illustrate this point, I'll just give you a very, very simple example. We'll run through it, we'll identify Nash equilibrium in the same way. But you'll see this next example will be a non-strict Nash equilibrium, as opposed to the strict Nash equilibrium that we've seen previously. So, have we finished with that page? Yep. Okay, that's, okay, just a very, very simple abstract game with ones and zeros. We've got player one, who chooses over two potential strategies of up and down. And we have player two, who chooses over three potential strategies of left, middle, and right. Remember, this is how we represent our games in normal form. So we've got the players, player one, player two, we've got the available strategies, up, down, left, middle, and right, and then we have the payoffs from those various strategy combinations. So, how did we say that we'd identify a Nash equilibrium? Well, our rubric was, we took each potential strategy of one player, and then looked for the optimal strategy of the other player. So, let's take player two as our starting point. If player two were to choose left, what would be the optimal response from player one? And remember, just to remind you, hopefully it's sinking in now, when we represent these games in normal form, the way in which we present the preferences, the way in which we present the outcomes are for the row player first, so that's player one is the first figure, and the column player, in this case player two, is the second figure. So if player two chooses left, we're looking down that first column there, that left-hand side column. Player one chooses up or down. Which one? Yeah, either. It makes no difference. Both of them would give a payoff of 1. So what's the optimal response? Well, they both are. So using that convention that we've adopted before, we'll put the circle around both of them. They're both optimal responses. If player 2 is going to choose left, it makes no difference whatsoever for player 1 whether he chooses up and receives a payoff of 1 or down and receives a payoff of 1. They're both optimal responses. Hence, put the circle around both of them. Were, though, player 2 to choose middle, what would player 1 do? Top. Yep. Or top would choose actually up. Yep, I get the idea. Up gives a payoff of 1. Down gives a payoff of 0. Which one do you prefer? 1 is obviously preferred to 0. And so, we put the circle around the 1. That's our optimal response. Then lastly, for player 2, if he chose right, the optimal response from player 1 is to choose down with a payoff of 1 there, as opposed to up, which only gives a payoff of 0. And those are it, or that's it, for player 1. That's all of his optimal responses. And now we just turn it around and do the same for player 2. What are his optimal responses? So, were player 1 to choose up, if player 2 chooses left, gets a payoff of 1. If he chooses middle, he gets a payoff of 0. Chooses right, he gets a payoff of 1. And so his optimal response are left or right. What we know, again, this is the same sort of idea with a strictly dominated strategy. What we know player 2 wouldn't do is ever choose middle. It gives a payoff of 0. But would he play left? Would he play right? We don't know. They're both optimal responses. And so I'll put a circle around both of them. Then lastly, player 1, were he to choose down, what's player 2 going to do? Going to choose middle. Yep, that one there. Now, I asked you these. I know there's only ones and zeros, and even if I ask my kids, but which is bigger, a 1 or a 0? Obviously, they're going to get it as well. But that isn't the point. It's just making sure that you're looking at the correct numbers on this. Making sure you're looking at using the correct column or correct row, looking at the first figure or second figure. That's the important part. It's not necessarily knowing that 1 is greater than 0. I would hope we've all got to the stage now that that shouldn't be too taxing for you. So please don't think I'm insulting you when I do ask you these questions. So, what have we got? We've got our game, we've identified the optimal responses, and what was our definition of a Nash equilibrium? It's that outcome where all players within the game are choosing the best response, given the actions of the other player. So where does that occur? Well, there's only one outcome here that is a Nash equilibrium. That accords with that principle. And that is where player 1 chooses up and player 2 chooses left. All of the other squares, segments, because they've either got a single, actually because they've only got a single circle, means that only one of the players is choosing a best response. And so the other player would have an incentive to deviate. Other player has an incentive to deviate because he's not choosing an optimal response. It cannot be a Nash equilibrium. So the only Nash equilibrium is that there, up, left. But this is a non-strict Nash equilibrium. Still a Nash equilibrium. No player has an incentive to deviate. But this one is non-strict. Why is it non-strict? Because no player has an incentive to deviate, but it does not mean that either of the players deviated, they would be worse off. So, for example, let's look at that outcome there. Does player 1 have an incentive to deviate? Well, the obvious answer must be player 1 cannot have the incentive to deviate because it is a Nash equilibrium. Would he categorically be worse off by deviating? Well, if player 2 is going to choose left, and player 1 at the Nash equilibrium gets a payoff of 1, what would happen if player 1 switched from playing up to down? His payoff would go from 1 to 1. It would be exactly the same. So, he's no better off. Does he have an incentive to deviate? No. You only have an incentive to deviate if you're better off. But this deviating player will be no worse off. And likewise, if we looked for player 2, given the Nash equilibrium at up and left, player 2 gets a payoff of 1. But if he switched from playing left to right, he would also get a payoff of 1. Now, is that an incentive to deviate? No. But is he worse off? No. Hence, that's a non-strict Nash equilibrium. But just a point to remember, this non-strict Nash equilibrium, it does not have to apply for both players. We could have had the outcome where player 2, if he deviated, was worse off. It would still be a non-strict Nash equilibrium. All it requires is one of the players to be no better off from deviating. But that's the idea. That's that distinction between a strict and a non-strict Nash equilibrium. And this concept, we're going to be pulling upon it in our penultimate, or maybe topic 6. Towards the end of this course, we're going to use this distinction between strict and non-strict Nash equilibria when we look at the idea of evolutionary stability. For the moment, just understand the concept, but we will use it at some time later. Now, we're still going to be dealing with static games of complete information, but what I now want to do is move it on ever so slightly. Because again, I keep on telling you things that I haven't told you before. I say, well, we haven't, all the Nash equilibrium that you covered previously were strict Nash equilibrium. Now I've told you about non-strict. What I also want to tell you is everything that you've studied up until this point, all the strategies are what are known as pure strategies. And with a pure strategy, think about the games that we've got. We might have had our prisoners who wanted to deny or confess. We had our two students, did they work hard or shirk? Or we had someone who chose up or down, or left or centre or right. These are pure strategies. Players looked at their available strategies, they've looked at their payoffs, and they've chosen a very, very specific choice. Do they shirk or do they work hard? Do they deny or do they confess? Those are pure strategies. What I now want you to do, though, is consider, and in a few moments, I'll tell you what a mixed strategy is, but to put it into context, I want you to consider this following game. And this following game is known as matching pennies. And matching pennies, like all of the games we've seen up until this point, is a very, very simple game. And in matching pennies, we have two players. And our two players are Bill and Ben. And what they need to do, they both got a coin, and they need to show one of the faces of those coins. Each of them chooses, do I show a head or do I show a tail? That's the game. So that's what they choose. So they're choosing over their pure strategies. Do they show a head or do they show a tail? And they're doing this at the same time. It's a simultaneous game, it's a static game. Heads or tails. That's all it is. However, if both show exactly the same face, if they both show a head or they both show a tail, Ben will win the coins. He keeps his own coin and he wins the coin off Bill. So if they're both the same, both heads or both tails, Ben will win. The alternative is what happens if one shows a head, at the other time the other shows a tail. But if that's the case, it's Bill who wins the game. So this is our game of matching pennies. Heads or tails. If they're the same, Ben wins. If they're different, Bill wins. Now in the same way as all the way through, and I've told you the sorts of things that I'd expect you to be able to do in an exam. I'll give you a game discursively. And they said, okay, now set this up in its normal form. So, this game of matching pennies, I've told you what the game is. Now, I'm going to represent it for you in its normal form. It's very, very straightforward. So, normal form. We want the players, we want the strategies, and we want the payoffs. Now, for any game, those first two for you should always, always be straightforward. We know who the players are, we know what the strategies are. It's these numbers in the middle that might potentially cause confusion. Now, this is a straightforward game. The payoffs for Bill or Ben are either +1 or -1. If they win the game, you get one coin, that's +1. If you lose the game, you lose the coin. So your payoff is -1. So we said when the coins were different, Bill would win. So therefore, if Bill chooses a tail at the same time as Ben chooses heads, he gets a payoff of +1. If Bill chooses the head at the same time as Ben chooses tail, Bill gets a payoff of +1. In the other instances, where they're both the same, that's when Ben wins. Well, Bill's payoff would be -1. He loses the coin there, or he loses the coin there. So for each player, the payoffs are just +1 or -1. And then for Ben, remember, Ben's payoffs are the second one. Ben wins when they're both the same, 2 heads there, or 2 tails there. Other instances, he loses, or he loses. So that's our game of matching pennies. So, where's the Nash equilibrium? How would we identify the Nash equilibrium? Well, use exactly that same rubric as we've seen before. For each player and each possible strategy of that player, what's the optimal response of the other? We've done it before, it's straightforward. So I'll go through this really, really quickly. So, for Ben, if he chose heads, what would Bill want to do? If he also chose heads, he gets a payoff of -1. If he chooses tails, he gets a payoff of 1. So obviously, he would rather choose tail. And so we put the circle around that. If Ben chooses tails, what's the optimum response for Bill? Well, if he chooses head, he gets a payoff of 1. Tails gives a payoff of -1. So obviously, choosing heads, the payoff of 1 is his optimal response. So again, the circle around it denotes his optimal response. Then we'll do the optimal responses for Ben. If Bill were to choose heads, what does Ben want to do? Now remember, Ben wants them to be the same. If they're the same, he wins. So if Ben chooses heads, the optimal response from Bill, if Bill chooses heads, the optimal response from Ben is also to choose heads. So that's what he would do. That gives him a payoff of +1 as opposed to -1 there. So circle around the 1 denotes an optimal response. And then lastly, if Bill chooses tails, what would Ben want to do? Also choose tails to match them. So there you go, chooses tails there, and he gets his payoff of 1. So that's his optimal response. So that's what we do. That's how we identify the Nash equilibrium. And so the Nash equilibrium is where both circles go inside. Hold on. No. What's wrong? Have I made a mistake? Where's the Nash equilibrium? I said, our Nash equilibrium is that instance where all players are choosing an optimal response. That's where both circles would coincide. Two circles aren't coinciding there, which is a little bit problematic, because again, something else I've also told you in a previous lecture. In every finite game, there will always be at least one Nash equilibrium. And yet in this game of matching pennies, it doesn't seem to be. So, you've been studying game theory 2 and a bit weeks. In that 2 and a bit weeks, have you disproved the Nash theorem? Do you think that's what the answer was? It's not going to be that, is it? The alternative is that I've made a mistake. Oh, seriously. Oh, that isn't going to happen, is it? So it isn't that either. So, I've not made a mistake. You've not disproved the Nash theorem. The only plausible outcome, the only plausible answer, is that there's something else that I've not told you. And of course, that's what it is. Because in this game here, absolutely, there is a Nash equilibrium. And the Nash equilibrium is where both Bill and Ben choose their strategies, choose to play heads or tails with a probability of 1/2. That will be the Nash equilibrium. That will be a mixed strategy Nash equilibrium. As I said previously, everything that we've seen up until this point was a pure strategy Nash equilibrium. This Nash equilibrium in this game of matching pennies is a mixed strategy Nash equilibrium. Now I'm hoping everything that we've done, not just today, but everything that we've done previously, that you're all very, very comfortable with what a Nash equilibrium is, with the idea of a Nash equilibrium. That given their available strategies, all players are choosing an optimal strategy. That's the Nash equilibrium part, and that will never ever change. Something different now though, I've introduced that idea of a mixed strategy. What then is a mixed strategy? Well, just to give you a definition to start you off. A mixed strategy is the probability distribution over all or some of a player's available pure strategies. Now the important one, it's all important. This is the part I want you to really, really pay notice of. It's a probability distribution. It might not resonate with you for the moment, but as we move on, as we move through seminars, as we move towards your exam as well, I want you to remember that. A mixed strategy is not a probability. It is not a probability. It's a probability distribution. If you remember that, you won't make a mistake. And you won't throw away silly marks in the exam. Just quoting a probability back to me, it's not a mixed strategy. If I ask you for the mixed strategy and you tell me a certain probability, that's wrong. Okay? So don't do it. Probability distribution. What, though, do I mean by a probability distribution? Well, just to give you some examples. So, in that game of matching pennies, there are 2 pure strategies. To play heads or tails. Those are the pure strategies available to both Bill and Ben. And so we said a mixed strategy was the probability distribution over all or some of the available pure strategies. Well, given those pure strategies of heads and tails, a mixed strategy would be P 1 minus P, where we said P is the probability that the player chooses heads, and if you play heads with a probability P, the rest of the time you play tails. If you play heads with a probability of P, the rest of the time is 1 minus P. So, the mixed strategy for either player is that probability distribution over which you play heads, P, or tails, 1 minus P. And what do we notice about that probability distribution? What's the most obvious thing about any probability distribution as I've set it up? Any mixed strategy? It will always sum to 1. Yep. You've got to do something. You either play heads or you either play tails. You either choose up or you either choose down. You either shirk or you either work hard. Players have got to do something. So if you sum over all of those, it must equal 1. So again, if you've identified a mixed strategy and you quote it back to me, and that probability distribution does not sum to 1, it can't be correct. Yeah? It's always sum to 1. So, that's what it is. That's what it's in as a very, very general form. And I'll just give you some very, very specific examples now. Let's say we had a mixed strategy of 0, 1. Again, looking at this idea over heads or tails. So the mixed strategy of 0, 1 means that we attach a probability of 0 to playing heads. So how often do you play heads? Never. We attach a probability of 1 to playing tails. With a probability of 1 means you always do it. So if either of the players chose that mixed strategy, 0, 1, that's synonymous, that's exactly the same as always choosing to play tails. That's the pure strategy of playing tails. And, in the same way, the mixed strategy 1, 0, for either of the players, means that they attach a probability of 1 to playing heads, and a probability of 0 to playing tails. So they never play tails. They always choose heads. That is the pure strategy of playing heads. But don't think of mixed strategies and pure strategies as being different things. One is just a subset of the other. And just give you a few more examples. Something else, again, that we would have thrown out previously, where one of the players would have chosen between left, centre and right. The way in which we present this mixed strategy would be the probability distribution over these pure strategies. So the pure strategies are left with a probability of P, centre with a probability of Q, and right, well, with whatever's left. So 1 minus P minus Q. That's the part that's left. You either play left, or you play centre, or you play right. And if I were to add all those three probabilities together, what would I get? 1. So you've got P, Q, minus P, minus Q. They drop out. What we're left with? 1. Probability distribution sums always to 1. So, for example, the mixed strategy, 1/3, 1/3, 1/3, would assign an equal weight to all of these available pure strategies. And that would be a potential mixed strategy. And in the same way, the mixed strategy of 0, 0, 1 would mean that you attach a probability of 0 to playing centre. Sorry, a probability of 0 to playing left, a probability of 0 to playing centre, and a probability of 1 to play right. So, that is exactly the same as the pure strategy of playing right. So, that's what a mixed strategy is, that probability distribution. So, it's all very well. I've given you that definition of a mixed strategy Nash equilibrium, and I've bandied some probabilities around. I've talked about halves, I've talked about a third, I've talked about ones and zeros. As you should appreciate, or hopefully, as you would appreciate, in order to identify the mixed strategy Nash equilibrium, we need to arrive at a very, very specific set of probabilities. And it's that specific set of probabilities that lead to the Nash equilibrium outcome. So that's going to be our next part. And I'll just start this before I give you that 10-minute break. How do we identify that mixed strategy Nash equilibrium? And for the moment, I gave you that game of matching pennies, and I said the mixed strategy Nash equilibrium was where both players choose heads or tails with a probability of 1/2. I didn't say probability of 1/4, or probability of 1/3, or probability of 2/5. I said a very, very specific probability. And that's what we need to identify for this mixed strategy Nash equilibrium. But how do we identify it? Well, what we need to consider when we look at mixed strategies is that there's uncertainty. That the players aren't playing definitively one strategy or another. That they're looking at randomizing what they do. That their fellow players don't know for sure what they're going to do. Therefore, can they have a guaranteed payoff? If you don't know what your fellow players are going to do, you can't. All you can have is an expected payoff because of this random element, because you don't know what your opponent is going to do. So, we've said previously what players will want to do is choose a strategy, choose an outcome that gives them the best response, an optimal response, so they maximise their payoffs. Well, the same sort of idea here, but when we deal with mixed strategies, players will want to choose a strategy that maximises their expected payoff. Okay, before you go, I'm going to ask you one very, very simple question. I'll get you to use your phones again in a few moments, but I'm hoping that you all get this one right, but it's just to make sure that you do follow the logic through, and we're going to use this when we start off again after our break. So let's say that we have a certain outcome. It's outcome 1. And there's a 50-50 chance of this outcome yielding either a payoff of 10 or a payoff of 5. Okay? That's what it is. Certain outcome. 50-50 chance. Payoff of 5 or payoff of 10. What I want you to identify is the expected payoff. Right? So, it's all to do with contingent payoffs. It's an outcome, it's a payoff multiplied by the probability of that outcome occurring. So, we said it's a 50-50 chance. So half the time there's a payoff of 10, half the time there's a payoff of 5. So what we do is we calculate the contingent payoffs. 10 with a probability of a half, 5 with a probability of a half. Yep, so 10 times 0.5 is 5, 5 times 0.5 is 2.5, 5, you add the contingent payoffs, 5 and 2.5, so your expected payoff is 7.5 there. So, I've introduced the idea of a mixed strategy Nash equilibrium. We've bandied some probabilities around, but now what we need to do is arrive at that definitive set of probabilities, those specific set of probabilities that lead to a mixed strategy Nash equilibrium. So, how do we do that? Well, the part that doesn't change is what a Nash equilibrium is. A Nash equilibrium means that players are choosing an optimal response, a best strategy. This time, though, the best strategy will be in terms of a mixed strategy. So each player will be choosing a mixed strategy that is a best response to the mixed strategy chosen by all other players within the game. So that basic idea does not change. But how do you identify the best response that is a mixed strategy? Well, remember what we said? We need to adopt that principle that each player wants to maximise their expected payoff. So, that's a starting point. How do we identify the expected payoffs? Well, in order to identify these, we need to know something about the player's beliefs. For each player, what they think the other player is going to do. So, what I'm going to do for the moment, I'm going to put a bit of notation down. And it's really, really straightforward. It probably will take you longer to copy this slide down than it really involves the effort. Very, very simple, just to get the notation in. And I'll do it once, just for this example. All examples of mixed strategies from here on in, I won't go through the formality of putting anything like this down. What we'll say, though, is Bill and Ben are playing this game. They don't know what their fellow is going to do. Bill's got to think, well, okay, do I play heads or tails? And what I will choose to do will be influenced by what I think Ben is going to do. And we're going to say that Bill thinks that his opponent Ben will choose heads with a probability of P, whatever P is. He thinks he will choose heads with a probability of P. And by extension, if he thinks that his opponent will play heads with a probability of P, the rest of the time he thinks that he's going to play tails with a probability of 1 minus P. So that's his beliefs, that's Bill. That's what he thinks his opponent will do. Play heads with a probability of P, and tails with a probability of 1 minus P. For Ben, pretty much the same. He thinks that his opponent will choose heads or tails with a certain probability, whatever that might be. And we'll say that Ben thinks that Bill will play heads with a probability of Q. P and Q, we're setting them as different. P is the probability that Ben will play heads. Q is the probability with which Bill will play heads. So, if Ben thinks that Bill will play heads with a probability of Q, the rest of the time, that is with a probability of 1 minus Q, he's going to be choosing to play tails. And that's all we need to say about the player's beliefs. That it's believed that Ben will play heads with a probability P, tails with a probability of 1 minus P, and it's believed that Bill will play heads with a probability of Q, and tails with a probability of 1 minus Q. So I said, it's a very, very formal way to set this up, and I won't ever give you a page of beliefs that look like that again. But what I'm now going to do is take those beliefs and add them to that game that we set up previously in its normal form. So, that's the game that we've got. That was in its normal form. The only difference is I've now appended on these probabilities of P and 1 minus P and Q and 1 minus Q. It's the only difference. Remember what we said? We said that Ben thought that Bill would play heads with a probability of Q. He thought that he would play tails with a probability of 1 minus Q. Likewise, Bill thinks that Ben will play heads with a probability of P, and he will play tails with a probability of 1 minus P. That's the only difference. And whenever we see these in the future, we'll jump straight to something like this. So now we've got everything in place that we need to identify the mixed strategy Nash equilibrium. It's based upon the idea that players want to maximise their expected payoffs. So, what are the expected payoffs for Bill and Ben? Well, we'll take it in order. We'll do Bill first of all. So Bill either chooses heads or he chooses tails. That's all he can do. We want to know, if he chooses heads, what can he expect to receive as a payoff? And if he chooses tails, what can he expect to receive as a payoff? Now this is all based upon what we saw previously, these contingent payoffs. Payoffs weighted by the probability of that payoff occurring. So, for Bill, if he chooses heads, he either gets a payoff of -1 or he gets a payoff of 1. That's the only two outcomes. You either lose the coin and get a payoff of -1, or you win the coin and get a payoff of +1. Those are the only two things that could happen. But what are the probabilities of those two things happening? Well, if Bill thinks his opponent will choose heads with a probability P, he believes with a probability P he's going to get a payoff of -1, that he will lose. If he thinks that his opponent is going to choose tails with a probability of 1 minus P, he will get a payoff of 1 with that probability of 1 minus P. That's when he wins. And so the expected payoff is -1 with a probability of P, -1 with a probability of P, contingent payoff, plus 1 with a probability of 1 minus P, the other part of the contingent payoff, and we just add them together. And that gives us his expected payoff. So whenever Bill chooses heads, he would expect his payoff to be, just simplify that a little bit, so that's -1 times P, so it's minus P, plus 1 minus P again. So 1 minus 2P. So that's the expected payoff for Bill from choosing heads. That's what he can expect to receive. And remember, it's related to P, the probability that his opponent chooses heads. So that's his expected payoff of choosing heads. Were, though, in contrast, he were to play tails, what would his expected payoff be? Well, if he chooses tails, Bill will either get a payoff of 1 or he's going to get a payoff of -1. So only one or the other. He wins and gets a payoff of 1, and he will win with a probability P, or he loses, gets a payoff of -1, and he loses with a probability of 1 minus P. And so, the expected payoff is 1 with a probability P, contingent payoff there, plus -1 with a probability of 1 minus P. Simplify that through, you've got P times 1 is P, -1 plus P. So P plus P is 2P, -1 is -1. Just simplifying it at the end. So there you go. That's the expected payoff of playing tails. So now we know for Bill what he can expect if he chooses to play heads. We know what he can expect to receive if he chooses to play tails. Now, the trick to finding the mixed strategy Nash equilibrium is to equate those two. Okay, let's equate the two, but we'll do it for Ben first of all. Okay, so about that. So let's run through it for Ben. So for Ben, and I'll do this one really, really quickly, hopefully you get the idea now. Ben can choose either heads or tails. If he chooses heads, he either gets a payoff of 1 with a probability of Q, or -1 with a probability of 1 minus Q. He gets 1 if he chooses heads, -1 if he chooses tails. And he expects his opponent to choose heads with a probability of Q. He expects his opponent to choose tails with a probability of 1 minus Q. So there you go. That's 1 times Q plus -1 times 1 minus Q. Those are contingent payoffs. We add them together. And so the expected payoff for Ben from choosing heads is 2Q minus 1. And then lastly, were Ben to choose tails, what can he expect? Well, he either gets a payoff of -1 or he gets a payoff of 1. -1 with a probability of Q, or 1 with a probability of 1 minus Q. So -1 with a probability of Q, 1 with a probability of 1 minus Q. Simplified out, and there you go. His expected payoff is 1 minus 2Q. So for both Bill and Ben, we know their expected payoffs. Now comes the part where I prematurely started. To identify the mixed strategy Nash equilibrium, the trick involved is equating these, everyone's finished with that? Is equating these expected payoffs. Now, in a moment, I'll tell you why we do that. Initially, though, we'll just go through the mechanics of it. So you take, for both Bill and Ben, you take their expected payoffs and you equate them. So for Bill, you equate his expected payoff of playing heads or tails. For Ben, you would also equate his expected payoffs of heads or tails. And that will give you a crucial probability. So let's do it for Bill. We said for Bill, his expected payoff from choosing heads was 1 minus 2p. That's what we showed previously. We said his expected payoff from choosing tails was 2p minus 1. So, that's what you do. You equate them. So, 1 minus 2p equals 2p minus 1. And just solve that. Work it through. We want to find what p is. And that tells us that when p equals 1/2, the expected payoff from choosing heads is equated with the expected payoff from choosing tails. Only when p exactly equals 1/2. But we're talking about Bill. What is p? Remember? P was the probability with which who chose to play heads? Is it Bill? Exactly. P is the probability with which his rival chooses to play heads. His expected payoff, it's not what he does that's important, it's what the rival does. And when you calculate these expected payoffs, that's what should be in there. It's not what the individual is doing, it's what their opponent is doing. That's what determines the payoff for Bill or Ben. It's what their rival does. So, whenever Ben plays heads with a probability of half, Bill will get exactly the same payoff from heads or tails. What would he rather do then? Play heads or tails? Exactly. He would be indifferent. Whenever P equals a half, whenever Ben plays heads with a probability of half, Ben is absolutely indifferent. And what does that mean? What's his optimal strategy? What would his optimal strategy be if he's indifferent? Anything. It makes no difference what he does. It makes no difference to Bill whether he chooses heads or he chooses tails or any combination or any probability of heads or tails, because he gets exactly the same payoff whenever Bill plays heads with a probability of 1/2. So anything, everything is optimal. However, what would happen if P wasn't exactly equal to a half? So we know what happens if it exactly does equal half. The expected payoffs are the same. And if the expected payoffs are the same sort of idea when we looked at these non-strict Nash equilibria. We get multiple things that are optimal. In this scenario, it just means everything's optimal. It doesn't matter what Bill chooses to do. But what happens when it exactly doesn't equal a half? This is the important part. What will Bill choose to do? Well, what we can do is let's take any value that isn't equal to a half. I skipped over that a bit quickly. Anyone copy that down? Let's see what happens when P exactly isn't equal to a half. And it doesn't matter what that value is, it will mean that Bill is not indifferent. So, let's think about it. Let's take a value less than half. Let's take a value greater than half. So, what value could we take less than a half? Give me a suggestion. Any value less than a half? 0. Or we could choose 0.1, 0.2, we could choose a quarter, 2/5, whatever. They're all values less than a half. But that's the exact thing. Let's make it nice and easy for ourselves. And what about value greater than a half? Well, we could take 4/5. We could take 3/4. We could take 7/8. We could take 1. And that's what we're going to make it easy for ourselves. Any value less than a half will get exactly the same. Any value greater than a half will find exactly the same. So, let's say P is less than a half. And any value that we take for P is less than a half, we'll find that the expected payoff from choosing heads will be greater than the expected payoff from choosing tails. So if you're Bill, and your expected payoff from choosing heads is greater than your expected payoff from choosing tails, what would you choose to do? Always play heads. Now if you're always playing heads, is that a mixed strategy? Sort of. But it's a pure strategy. Yeah? If you always play heads. So, let's take, just to show you why that's the case. So let's take, or we could take any value less than half. So let's take that value of 0. So when P equals 0, what's the expected payoff from playing heads? Well, it was 1 minus 2P. When P equals 0, that's 1 minus 2 times 0, 1 minus 0 is 1. So when P equals 0, or when P equals 0, the expected payoff from choosing heads is 1. But when P equals 0, the expected payoff from choosing tails, which is 2P minus 1, 2 times P, 0 minus 1, so the payoff is minus 1. So when P equals 0, that is Ben plays heads with a probability of 0. What gives the higher payoff? Heads gives a payoff of 1, tails gives a payoff of 0. If you think about it intuitively, what did we say? We said Bill wanted the coins to be different. So if he plays heads with, if Ben plays heads with a probability of 0, that means he never plays heads. Ben will always choose to play tails. So if Ben is always choosing to play tails, what will Bill want to do? always choose heads. He wants them to be different. There you go. That's what we said here. Whenever P is less than a half, Bill will always play heads. It's not just a mechanical process. Just think through the outcome that we're getting. Think through intuitively the outcome that we're getting. So, I've taken, or we've taken, that value as 0 as an extreme, but it makes no difference. You could put in any value of P that you liked. If it's less than a half, the expected payoff from choosing heads will always be greater than the expected payoff from choosing tails. Hence, that is what Bill will always choose to do. Now at the other extreme, what happens if P was greater than a half? You could take any value that you wanted and you'd find the same result. That for Bill, when P is greater than a half, the expected payoff from choosing tails is greater. So let's just take our extreme value, 1. That's greater than a half, so let's take that. Let's look at the expected payoff when P equals 1. Well, our expected payoff from heads was 1 minus 2P. When P equals 1, that's 1 minus 2, 2 times 1. So it gives an expected payoff of minus 1. The expected payoff from choosing tails, when P equals 1, it's 2 times 1. So it's 2 minus 1, gives a payoff of 1. Well, obviously, 1, choosing tails, is preferred to minus 1, choosing heads. And so, when P equals 1, Bill will choose to play tails. And indeed, any value greater than a half will always choose to play tails. So this is the idea. That's the principle we want to identify. When we look for that mixed strategy Nash equilibrium, why do we equate these expected payoffs? Because we want to find that probability at which Bill is indifferent. Because if we move away from that crucial probability, what happens? Bill plays a pure strategy. He either always plays heads or he always plays tails. And what's the problem with him playing a pure strategy? There is no Nash equilibrium in pure strategies. Therefore, that's why we need to find that crucial probability at which the player is indifferent. And that's why we equate them to find that crucial probability. So, that's it for Bill. We could do exactly the same for Ben. We'd find that crucial probability by equating the expected payoff for heads with the expected payoff for tails. You do that, it just happens to be that we get that exact same probability. This time though, the probability is not in terms of P, but it's in terms of Q. We're looking for Ben, but Q is the probability that Bill chooses heads. It's the probability with which his rival chooses his strategies. So that's the crucial probability. And then we could do exactly the same. What happens when Q is not exactly equal to a half? And we'll take our extreme values, 0 and 1. When Q is 0, for example, expected payoff from heads is minus 1. Expected payoff from tails is 1. So therefore you get a higher expected payoff from choosing tails. So that's what you'd always choose to do. When Q is greater than a half, let's take 1 as an example. The expected payoff from heads is 2 minus 1. It's 1. The expected payoff from tails is 1 minus 2. It's minus 1. You prefer 1 to 2. Therefore, you always choose to play heads. I'll run through that last bit a bit more quickly. But you can fill in the details for yourself. It's exactly the same as we saw previously for Bill. So now we know exactly what Bill is going to do. We know exactly what Ben is going to do. We know when they will do when it exactly equals a half, that probability. We know what they will do when it deviates from that crucial probability of half. So that's the setting up point. Now what I want to do, now what I want to introduce you to is this idea about best response lines. A graphical way of representing all that information. Now I would assume, and we'll do this in seminars as well, getting up until that point is straightforward. In an exam, if I asked you a question like this, I would expect you all to get that straightforward. Work through one or two examples, there's no reason why you shouldn't get that. This next part is the one part where students fall down. It is simple, but you've really got to think about what you're drawing in these diagrams. Okay? So, we're now going to represent all that information graphically to identify the mixed strategy Nash equilibrium. Okay? So for all of you, what I'd like you to do is copy this grid down. Okay? And then we're going to draw the best response lines on it. So, whenever you do these examples, all we have on the axes, for the moment, don't worry about the labels. I'll put the labels in just to make sure that you understand it. But these graphs, any time I'm going to ask you to draw these graphs, in seminars or in an exam, what we have on the axes are probabilities. That's all it is. We've got Q on this axis, probability Q, and we've got P on this axis. That's it. You've got to get the axes right first of all. So I'll spend a few minutes making sure you're clear what we're doing. If you're not clear with the axes, it's all going to fall apart. You're not going to get the right outcome. So, all this is an axis, two sets of probabilities. And we've only got two probabilities here. We've got P and Q. Okay? So you don't need to ask me questions later. It does not matter which axis you put these on. You could change these, put Q down here and P up there. If you did, the labels would change, the way in which you drew the diagrams would change, but in itself that doesn't matter. If the diagram's correct, it's correct, regardless of what you have on the axis. So what I've done, I put Q on that vertical axis, I put P on the horizontal axis. Now think about it. What was Q? When I set it up for you, what was Q? Q was the probability that Bill chose heads. Yep, you've got to get these the right way round. Q is a probability that Bill chooses heads. And hence, I've just put that label there. The label is only there for your understanding. It's not an integral part of the diagram as such. But Q was the probability that Bill chose to play heads. And P, our probability on the horizontal axis, was the probability that Ben chose to play heads. Okay? So again, these are in, just so you know what we're referring to. This is the probability that Bill moves. That's the probability that Ben moves. Now a probability, what does it run from? What's the minimum value it can take? 0. What's the maximum value it can take? 1. So these axes are running from 0 to 1. That there is the maximum value of P. That's P equals 1. That there is the maximum value of Q. Q equals 1. And likewise down here, that point there is where P equals 0. That point in the origin there is where Q equals 0. Again, go back to when we set up mixed strategies. If you play Q with a probability of 1, that means you always choose heads. You're playing the pure strategy of heads. So that maximum value of Q, Q equals 1, is where Bill is always choosing to play heads. So just put that there as a label for you. If we're at that point there, that means Bill is always choosing to play heads. That's Q equals 1. Doesn't do anything else, doesn't ever play tails. Q equals 1, he plays heads with a probability of 1. He's choosing that pure strategy of heads. At the other extreme, we've got Q equals 0 down here. That's the minimum value of Q. So, Q is the probability that Bill plays heads. Well, if he's playing heads with a probability of Q, or probability of 0, what does that mean he's doing? He's never ever playing heads. He's always choosing tails. And hence, that Q equals 0 there means that Bill is always choosing to play tails. And I put those labels in. If you put those labels in, you put them in correctly, the rest of it will all fall into place. But you need to set it up properly first of all. If you don't do that, you're going to encounter all sorts of problems. So it's easy when I'm standing here and doing it. So when you've got a blank piece of paper, you've got to construct this for yourself. That's when it becomes more difficult. If you've done a few of them, it will all, as I said, fall into place relatively straightforward. So that was Q, and then we've got P on this axis. P is the probability that Ben chooses heads. When P equals 1, it means Ben always chooses to play heads. When P equals 0, we're down here, he plays heads with a probability of 0. That is, he always chooses to play tails. So there you go. That's our axis. That's set up. Now that that's in place, then we can put the best response lines in. And so what we'll do is we'll start with Bill. So for Bill, what was crucial for Bill? It's that probability P. For Bill, what mattered was the probability with which Ben chose heads. And we identified that crucial probability, P equals a half. So there you go. I put that crucial probability in there. So, for Bill, what did we say would happen when P was less than a half? When P was less than a half, if you look back to your notes, we said that Bill would always choose to play heads. So, P equals a half. What part of the diagram are we looking at? Well, P equals a half is anywhere in that first left-hand side of the diagram. That's the sort of area that we're looking at. That's P equals a half. So when P equals a half, Bill always chooses to play heads. Well, how do we denote that? Well, there you go. If he's always playing heads, that is what we're looking at there, that part of the diagram. And it doesn't matter what value of Q, it could be 0, or it could be any value less than a half. He will always choose to play heads. And so, that's the first part of his best response line. Doesn't matter what the value of P is, if it's less than a half, he will always choose to play heads. So that's his best response line. That traces out his optimal response. Now the next part. What happens if P was greater than a half? Well, if we're looking for P greater than a half, we're looking at the right-hand side of the diagram. That sort of area there. And we said, whatever value of P it is, as long as it's greater than a half, there's a higher payoff, expected payoff for Bill from choosing tails than there is from choosing heads. And so he always chooses to play tails. So this is for Bill. We've put the label in, makes it nice and easy for us. So it doesn't matter what the value of P is, if it's greater than a half, Bill will always choose to play tails. And so there you go. That's the second part of his best response line. If Ben plays heads with a probability less than a half, Bill will always choose heads. If Ben plays heads with a probability greater than a half, he will always choose to play tails. And then the last bit, what happens when P was exactly equal to half? When Ben plays heads with a probability of half. What was the optimal response from Bill? What do we say it was? Both is partly correct. It's indifferent. You could play heads, that would be an optimal response there. You could play tails, that would be an optimal response. But absolutely anything is optimal. It doesn't matter what you do. It could be played with push-up heads or tails or any combination or probability of heads or tails. They would all be optimal. And hence, there you go. That line denotes all strategies are optimal. So there you go. That, for Bill, is his best response line. Now we just turn it around and do exactly the same for Ben. Now remember, for Ben, what mattered for him was the probability of Q, probability with which Bill chooses heads or tails. So, if we said that that crucial probability was Q equals a half, so there you go, I've drawn that crucial probability in there. Now what happens when Q was less, which way round have I got this? Yeah, what happens when Q was less than a half? Well, if we want to make Q less than a half, we're looking at the bottom part of the diagram. The bottom half of the diagram. Right? So this area here. Now we said, whenever Q was less than a half, doesn't matter what it is, we took 0 as an extreme value, but we said, look, that will apply to anything. Any value of Q less than a half, the expected payoff from tails was greater than the expected payoff from heads. So we said that Ben would always choose to play tails, whenever Q was less than a half. So in this bottom half of the diagram, that sort of space there, the optimal response is for Ben always to choose tails. See, as we're going up, it means that Q is getting bigger. But what is Ben still doing? Still playing tails. So that's the first part of his best response line. At the other extreme, what happens when Q is greater than a half? So we're looking at the top part of the diagram. We said whenever Q, whatever value of Q is greater than a half, Ben would always choose to play heads. That heads always gave a higher expected payoff. And hence, in this top half of the diagram then, that corresponds to any value of Q greater than a half. When that's the case, Ben will choose to play heads. We identified that he would always choose to play heads. And so, that's the next part of his best response line. And all we need to conclude this, what happens when Q was exactly equal to a half? When Q equals a half, Ben was indifferent. It made no difference what he did because he got exactly the same expected payoff. So all strategies are optimal. He could play heads, he could play tails, or any combination of the two. And hence, that's the final part of our best response. So, what does that suggest then? Well, think about what those best response lines are. They identify the optimal response of one player given the strategy chosen by the other. So that's what any individual best response line is. We've just plotted out graphically the optimal response, the optimal strategy of Bill given what Ben does. And we've plotted out the optimal strategy of Ben given what Bill does. So individually, each line shows an optimal strategy. Where they cross though, what does that mean? It means that both players are choosing optimal strategies. And what did that suggest? Both players within the game are choosing an optimal strategy, given what the other player is choosing, that is a Nash equilibrium. And so this point here in the diagram, where the two best response lines intersect, that identifies our Nash equilibrium outcome. And there is only one place where these best response lines intersect. Hence, there is only a single Nash equilibrium. And that Nash equilibrium means what? It means that Bill is choosing to play heads with a probability of Q, and by extension, he chooses tails with a probability of 1 minus Q. So he's playing the mixed strategy, 1/2, 1/2. And in the same way, Ben, in this Nash equilibrium, is choosing P with a probability of 1/2. So he's choosing heads with a probability of 1/2, and by extension, tails with a probability of 1/2. And that is our mixed strategy Nash equilibrium. And that's what I said right at the beginning. I said there is a Nash equilibrium in the game, and that is where both players choose to play heads with a probability of 1/2. That is what we've got there. But notice though how I've represented these mixed strategies. It's a probability distribution over their available, some or all of their available strategies. So the mixed strategy is for Bill to play, the mixed strategy Nash equilibrium is for Bill to play the mixed strategy 1/2, 1/2. That's his probability distribution. And it's also for Ben to play exactly the same mixed strategy, 1/2, 1/2. And that is the Nash equilibrium of this game. The mixed strategy Nash equilibrium of this game. Make sense? Okay. What I want to do before I give you one more example is just think about that intuitively. In fact, I might even save that second example till next week rather than rush it. But I'll give you this intuitive interpretation first of all. Think about it. We've got this game of matching pennies. And we said that the only Nash equilibrium in this is for both Bill and Ben to choose heads or tails with a probability of 1/2. Well, that's Bill and Ben randomising what they do. You must all get a coin, flip it, half the time it's going to come down heads, half the time it's going to come down tails. But it involves them randomising what they do. Is that something... We've talked about this in a very formal way. I've given this idea of a Nash equilibrium, and we've put a little bit of maths in there, but is this the sort of outcome that you would expect in the real world? That people, they behave with a random element. Is that what you would expect? Well, if you think through the logic of this game, the setup of this game of matching pennies, absolutely it is. I want to draw maybe another example just to really, really reinforce this. What we've got here in this game of matching pennies, and it's something I touched upon in our lecture last week when we talked about that game of the Battle of the Bismarck Sea. And I said, what we've got here is a zero-sum game. Now this game of matching pennies, again, is a zero-sum game. Now zero-sum games, as I mentioned last week, are games where the only way one player can benefit is at the direct expense of the other player. So in this game of matching pennies, there's only one thing at stake. There's a coin you can either win or you can lose. If Ben wins it, it means that Bill loses it, and vice versa. This is a classic zero-sum game. And in all games that are zero-sum, where there's this direct element of competition between players, no Nash equilibrium would ever exist. It could not ever exist in pure strategies. It could only ever lie in players randomising what they do. And I'll give you a very, very simple example here about a game of poker. Now in poker, what I want you to think about is what happens when a player is dealt a poor hand. Yep. They've got a run of cards and there's no way. They can't form any tricks. They can't possibly win. So think, what would that player want to do? Poker, well, card games, is a classic zero-sum game. The only way that you can win in poker is at the expense of the other players within the game. So, what would happen when a player is dealt a poor hand? Well, they've got two options. You can either fold or you can bluff. You can fold, in which case you don't compete against the other players, or you bluff, that you can pretend that you've got a stronger hand. And you get the other players to bid against you with the hope of winning. But you know your hand couldn't possibly win. So you could fold or bluff. So those are the available pure strategies. But I've said, look, this is a zero-sum game. It's this game of direct conflict. And I've said, intuitively, there is absolutely no way in a game of poker players could ever rationally play a pure strategy. So why is that the case? When a player gets a poor hand, why could that player never play a pure strategy? Could not ever either bluff all the time or fold all the time. Okay, let's take the first one. How about folding? Well, no, let's take the other. Let's do bluff first of all. So the one thing, every time you've got a poor hand, do you bluff? Do you pretend that you've got a stronger hand? Well, if you do that, in a game of poker, collectively, the other players in the game will have more winning hands than you. So every time you've got a poor hand, if you stay in the game and always bluff, you're going to lose out. Because the other players collectively would have more winning hands. So you can see, that couldn't possibly be an optimal strategy. That pure strategy of always bluffing could not possibly be optimal. You're going to lose out. The other players will have more winning hands than you. So that makes sense, okay? I can understand why you shouldn't always bluff. What about the other scenario? If you've got a poor hand, why don't you just fold? You're not going to be able to win. Why don't you just fold? Why don't you follow that pure strategy for always folding? Zach, were you going to tell us all why? Are you a card shark?
I don't know, but if you always fold, then that means whenever you play the game, then you've got a strong hand. So.
Exactly. If every time you've got a poor hand, you fold, you don't bid against other players, you lose your stake, but you say, well, how could that possibly not be an optimal strategy? For exactly the point that Zach said. If every time you had a poor hand, you folded, what would that tell the other players in the game you had, if you remained in the game? That you had a strong hand. And if they know that you've got a strong hand, they won't bid against you. And therefore, you can't beat them. So you can see, in that scenario, there's no way that either of these pure strategies can ever be optimal. The only way in a game like this you can keep the other players honest is by randomising what you do. But you keep them honest by occasionally bluffing. Sometimes you bluff when you've not got a strong hand, but it's to keep the other players honest. And so to adopt a pure strategy makes no sense whatsoever. And so I've talked about poker here as an example, but you might think penalty takers in football, exactly the same thing. If a penalty taker always kicks the ball to the same side each and every time, eventually the goalie is going to read it. That's why you need to randomise what you do. In the same way with a pitcher in baseball, that you don't throw the same ball down all the time. To adopt a pure strategy is non-optimal. You've got to randomise what you do.